Hi, my name is Antonio Aguiar. I will explain the article called Cooperative Task Allocation for Multi-UAV System based on ACO, RSTAR, and DWA. In the introduction, the transport sector has shown growing interest in UAV applications. This interest has been driven by the growth of e-commerce, which has generated a demand for innovation logistics solutions. The UAVs have the ability to take off and land safely in the vicinity of buildings and people, which significantly improves the quality of transport service in congested or hard to reach regions and has the potential to revolutionize the way goods are transported, offering efficiency and agility. In the problem, the importance of efficient coordination in complex missions that involve optimization trajectories for several collaborative robots. In this context, task assignment must consider not only energy capacity of and obstacle avoidance constraint, but also efficiently integrate robot navigation and sensing to avoid collisions and plan efficient trajectories. The proposal is this study will apply a mathematical model based on the ant-colony optimization, the ACO technique. The mathematical model will consider the constraints of multiple travelers elements problem, MTSP, and we use the R-star algorithm to avoid fixing obstacle and dynamic window approach, DWA, for mobile obstacle. In additional, energy constraints will be added to the UAVs and the possibility to receive rewards when passing in waypoints. To apply the mathematical model, we have four main steps. First, we define a map. Then we pre-proceed it using a star to calculate the distance between waypoints, avoiding fixed obstacles. Then we apply ACR to designation, the order in which UAV visits the waypoints, taking into account UAV's constraints, such as the maximal distance it can travel, and the ability to receive rewards when visiting a waypoint. Finally, we use DWA to divert mobile obstacles, avoid possible damage to the UAV and missions failure. In this figure, we have the scenarios used in this article. We have 50 waypoints in yellow. Each waypoint will have a weight associated with its relevance. We also have some fixed obstacle marked in gray, and mobile obstacle. It also appear. It may represent unknown objects. In this figure, we will see a brief application of a star. In with case, we can go from waypoint 11 to waypoint 4 in a straight line because of the obstacle. So a star will calculate the route by avoid the obstacle. It's the wrong way and it's the possible path calculated by a star. About the ACO task allocation, the ACO algorithm is a heuristic algorithm that simulates the forange behavior of ants to find the optimal path. It was developed to solve the traveling elements problem and employs a positive feedback mechanism using pheromones to guide the algorithm in this search for the ideal solution. To deal with multiple targets and vehicles, the optimization process involves three main steps with ND and groups. The step one is the basic configuration and initialization. The step two is the solution building. And the step three, we have the pheromone update. After the execution of the all stages and the conclusion of the algorithm, the roads and the group in the group with the best result in NG are selected. And finally, we have the obstacle avoid with DWA. The DWA algorithm is commonly used to address the local trajectory planning problem for mobile robots. This method allows the robot velocity to be calculated at specific time intervals, which in turn facilitates the inference of the feasible motion trajectory of the next period. In addition, the DWA is able to determine the vehicle trajectory by using multiple evaluation functions. The DWA covers robot direction, velocity, and safety in the evaluation function. For the experiments, the simulations varied in the number of UAVs in each instance, with experiments ranging from 2 to 6 UAVs. In all experiments, the collaborative UAV starts the task from the initial depot and finish the mission by visiting the final depot, while respecting the energy constraint in terms of the maximum flight distance and weight collection, which we define. The simulations are the experiments we implemented with MATLAB on a CPU Intel Core i7 and 16 gigabytes of RAM. The UAV will have the maximum flight with Dmax equals to 28.6 meters, which represents the energy limitation for flight. Then you also have a maximum rewards collection capability of 8 points when visiting points. For the results, the table illustrates the results and comparisons of the experiments. The result shows that the total distance traveled by the UAVs increased as the number of vehicles increases, showing a steady increase and a moderate standard deviation. This was an unexpected result given the number of agents involved in the mission. The total time of the mission remained relatively stable regardless of the numbers of the UAVs, indicating that the number of UAVs along with the imposed restriction and adopted map does not experience significant variations, wherever the processing time showing a significant increase with the addition of the more UAVs, reflecting the increased complexity of coordination between vehicles. These results are critical to understand the performance and limitations of the UAV systems and provide valuable information for optimization in real missions. And in this figure, we have the image of the two AVs and four AVs in this figure. For the conclusion and future works, well, this paper makes four significant contributions. Firstly, we use a method that combines ACR, A star, and DWA to solve the MTSP with multiple constraints. This approach takes advantage of the strengths of each algorithm in order to improve solutions in the context of this problem. Secondly, the ability of DWA to act through its evaluation function in the avoidance of moving obstacles makes the proposed model more robust, being applicable in complex scenarios in aerial and terrestrial robots. Thirdly, we validate the algorithm in fictitious scenarios with sparse points and adding limitations on the UAVs. Finally, the algorithm can be used to analyze the feasibility of carrying out missions and can indicate the ideal number of UAVs. The research highlights the importance of efficient coordinates in missions with multiple collaborative robots, emphasizing the need to efficiently integrate navigation and system for collision avoid and efficient road planning. The results obtained in the simulations confirm that the approach is promising for improving efficiently and safely in UAV operations, making a significant contribution to the field of logistics and the freight transportation. For future works, we pretend check the applicability of the other optimization algorithms, such as DA and PSO instead of ACL for waypoint designation, and add mobile waypoint simulating UAV charging stations, and carry out practical tasks using real UAVs in a controllable scenario. Our thanks to the partners listed below. Thanks you for watching this presentation.